That's sound, the low groan of steel under pressure. If you have ever been near the top of a skyscraper in a storm, you have heard it. And something in you says, run. But here is what that instinct gets completely wrong. That sound is not the building failing. That is the building working. And if it ever went completely silent and still, that is when you would actually be in danger. Most people assume tall buildings work through sheer rigidity. Steel, concrete, locked in place, refusing to move no matter what the wind does. That model is wrong, and engineers nearly paid for it with catastrophic failures. When wind hits a tall building, it does not just push against one side. It flows around the structure and creates spinning columns of air called vortices, alternating back and forth, applying sideways force with every cycle. If those forces build up without somewhere to go, the building starts absorbing wind energy. The oscillations grow. And if nothing interrupts that cycle, you push the structure beyond what it was designed to handle. We do not have to imagine what that looks like. We have footage. The Tacoma Narrows Bridge in Washington State opened in July of 1940. 4 months later, it was at the bottom of Puget Sound. 42 miles per hour of wind. That is it. Not a hurricane. Not a once-in-a-century event. A moderate November morning triggered something called aeroelastic flutter, a self-reinforcing cycle where the bridge's own movement amplified the forces acting on it. The deck began to twist, gently at first, then in violent 45-degree arcs. At 11:10 a.m. on November 7, 1940, it tore apart and collapsed. Engineers had built something elegant and slender without fully understanding what happens when a structure has nowhere to put the energy it is being given. That morning changed structural engineering forever. The instinct after a failure like that is to build stiffer, heavier, more resistant. But engineers kept running into the same problem. The stiffer you make a structure, the more load it attracts. You are not reducing the forces acting on the building. You are concentrating them into something with less capacity to absorb them. Metal fatigues under repeated stress. Connections weaken over thousands of load cycles. A building that refuses to yield is spending its structural life every time a storm passes through. The real insight was not about making buildings stronger in the traditional sense. It was about making them smarter about how they handle the energy they cannot avoid. To understand what that looks like in practice, you need to understand what happens without it. Wind begins pushing a tall building. The structure oscillates a few inches at first. The vortices keep coming. The oscillations build. On the upper floors, occupants start feeling it. The building may be moving several feet in each direction. Structural connections are cycling through stress loads they were designed to handle, but just barely. Now, add a typhoon on top of that baseline movement, or an earthquake, while the wind is already pushing the structure toward its limits. The margin between uncomfortable and catastrophic is measured in inches. That is the problem engineers had to solve for buildings designed to stand 100 years in places where typhoons and earthquakes are not emergencies. They are just the calendar. Their solution is one of the stranger things you will ever see inside a building. Between floors 87 and 92 of Taipei 101 in Taiwan hangs a steel sphere weighing 660 metric tons, roughly the same as 90 adult elephants. It is 18 feet in diameter, made of 41 circular steel plates welded together, suspended from high-strength cables. It can swing up to 5 feet in any direction. When wind pushes the building east, the sphere swings west. The inertia of 660 tons of steel moving in opposition absorbs the oscillation before occupants ever feel it. 8 hydraulic dampers at the base convert that kinetic energy into heat, bleeding off the force rather than letting it accumulate. The system reduces the tower's movement by up to 40% during typhoons. Taipei 101 sits just 660 feet from a major fault line and was designed for winds of 134 miles per hour. Engineers were not being overcautious. They were building for a place where extreme forces are not a possibility. They are a certainty. During the 2008 Sichuan earthquake, visitors watched the damper swing in real time. During Typhoon Soudelor in 2015, it moved a full meter, the largest movement ever recorded. Both times the building held, not because it fought those forces, because it had a system for managing them. Different buildings solve the same problem differently. The Shanghai Tower spirals upward in a 120-degree twist, confirmed by wind tunnel testing, to reduce wind loads by 24% compared to a conventional rectangular tower. That reduction saved an estimated $58 million in structural steel during construction. The Burj Khalifa uses a Y-shaped floor plan that disrupts vortex formation before those patterns can synchronize with the structure's natural frequency. The John Hancock Center in Chicago puts its structural bracing on the outside of the building, visible from the street. Every approach is different. The underlying logic is the same. You cannot fight the wind. You can only redirect it. And this is the part that changes everything. The buildings that feel most solid are not the most rigid structures ever built. They are the most carefully managed flexible systems ever built. Every sway is controlled. Every oscillation has somewhere to go. Every gust of wind gets absorbed and dissipated before it can accumulate into something dangerous. A building that refuses to yield is not safer. It is just storing up forces until something gives. The engineers who figured this out did not do it by making buildings tougher. They did it by accepting that some movement is inevitable and designing around that reality instead of against it. Next time you feel a tall building move, remember this. That is not a warning. That is the system working exactly as designed. Next week we are getting into the hidden reason airplane flight paths look wrong on every map you have ever seen, and the survival calculation engineers build into every single route. If that is the kind of thing that changes how you see the world, subscribe to The Reason It Works.